So, guys, let us continue with the discussion of the definite integrals. In the previous lecture, we learned about the definition of the definite integral, and then we reviewed some properties of the definite integral. Now, in this lecture, we're gonna get acquainted with a very important theorem, which is called the fundamental theorem of calculus. Now, in the section 3-2, we see the first part of this theorem. This fundamental theorem of calculus is a two-part theorem, and here we get introduced to the first part of it. Now, fundamental theorem of calculus part 1 says that if a function f of x is continuous on the interval from a to b, then the function s, which we define it as the integration from a to x of f of t dt, is continuous on the interval a to b and differentiable on the open interval from a to b, and its derivative is, here you should omit this f of x, the derivative of s, which is s prime of x, or d over dx of s, is equal to, as you know, d over dx of the integration from a to x of f of t dt, and that is f of x. Okay? This is what you learn in the part 1 of the fundamental theorem of calculus. So, the theorem says that if we have a function f of x which is continuous on an interval, then the function s, which we define it as the integration from a to x of f of t dt, has a derivative which is equal to f of x. Okay? Now, before we go to the proof of this part 1 of fundamental theorem of calculus, it is good for us to delve into the meaning of it. Now, the important part of this fundamental theorem of calculus part 1 is this equality. The equality that says d over dx of the integration from a to x of f of t dt is equal to f of x. And what is the meaning of this? The meaning of this is that the derivative and the integration somehow neutralize each other, right? We can say that the derivative operates as the reverse of the integration. So you see that the derivative of the integration becomes the integrand, right? But you have to be very careful when you want to say this. There are some constraints for this theorem. Now, in this theorem, the variable with respect to which we are doing the derivative has to be the upper limit of the integration. And the other important point is that this lower limit of the integration has to be a constant. Okay? And you see that this t in this equality is the dummy variable and has no important role. Okay, you could write anything instead of t. You could write m, n, you could write p, q, r, s, t, Hassan, Ali, whatever you wanted. This t here has no specific importance. Okay, so keep this equality in mind. D over dx of the integration from a to x of a function is equal to the function. Okay? Now, we're not going to prove this theorem here completely. We're going to give you a tentative proof. Okay? And this is how it goes. Look, we start by the definition of the derivative for the function s. We know that the s prime of x is equal to the limit of s of x plus h minus s of x over h when h goes to 0. Now, let's look at the function s. According to the definition that we have for s, it is the integration from a to x of f. Okay? Now, look at this graph here. If the function f is the function denoted with the blue line, then the function s, because it is equal to the integration from a to x of f, is equal to the area under the curve of f starting from a and finishing at x. So s of x is equal to this area in blue. Now, in the same way, s of x plus h is equal to this area under the curve of f starting from a finishing at x plus h, right? So in a way we can say that s of x plus h minus s of x is equal to the area under the graph of f between x and x plus h, which you see in the graph in red, right? So we can say that this difference in the s is approximately equal to f of x, which is the uh, length of this rectangle in red, times h, which is the width of this rectangle in red. So we can say s of x plus h minus s of x is approximately equal to f of x times h. So if you replace this, if you replace this with s of x plus h minus s of x into the s prime of x, we're gonna have s prime of x equal to the limit of f of x times h over h when h goes to 0, which is f of x. Okay? Now, part 1 of the fundamental theorem is actually saying that for every function f that is continuous on the interval a to b, then the integration from a to x of f can be considered as an antiderivative, right? That is, the integration from a to x of f of t dt is an antiderivative for f because its derivative according to the theorem is equal to f. In example 13, we use this fundamental theorem of calculus part 1 to solve some problems. And here we have some functions y which are in the form of integrations of some other functions, and their derivative is asked from us. Now, it says find d over dx for the following functions. In the part A, the function y is the integration from a to x of t3 plus 1 dt. Now, using the fundamental theorem of calculus part 1, we can say that dy over dx, which is d over dx of this integration, is going to be equal to this integrand evaluated at the uh, variable we're working with, or the upper limit of the integral. So instead of t3 plus 1, we say x3 plus 1, right? Which is our f of x, right? So if y is equal to this, dy over dx is equal to x3 plus 1. In part B, which is very similar to the part 1, y is equal to the integration from x to 5 of a function which is 3t sine of t dt. Now, we are supposed to find the derivative of y with respect to x, and d over dy, dx over d over dx of y is equal to d over dx of the integration from x to 5 of 3t sine of t dt. Now, if we want to use the fundamental theorem of calculus part 1, we have to make some changes in this definite integral that we have here. We have to make some changes in this integral. Why? Because if you look at the theorem, in the theorem, the integral starts with a constant and ends at the variable. But here it is reversed. So we have to make some changes in this integral in order to be able to use this theorem, right? Now, the change that we need to make is a very simple one, and it is just to reverse these limits of integration. And according to the properties of the definite integral, we know that we can do that if we add a negative sign to the integral. So d over dx of this integral is equal to d over dx of negative integration from 5 to x of 3t sine of t dt, right? And we have moved the negative sign from here to the outside of the derivative. We can do that, right? Now, for this part, d over dx of integration from a constant to x of a function of t dt, we can use the fundamental theorem of calculus part 1, which tells you that this is equal to this function of t evaluated at x, which is 3x sine of x. And in the final result, we have to include this negative sign. So minus 3x sine of x. Now, what do we have in part C? In part C, the function y that is given to us is equal to the integration from 1 to x2 of cotangent of t dt. Now, we want to calculate dy over dx, right? And in the fundamental theorem of calculus part 1, the upper limit of the integration was supposed to be equal to x, but here we have x2. So we need to make changes. What is the change that we need to make? It is this. Imagine this x2 to be equal to a function u, right? We are doing some change of variables. We're changing the variable. If we consider x2 as u, then y becomes integration from 1 to u of cotangent of t dt, right? Now, this new y is a function of u, right? And u as a function of x is equal to x2. So we can use the chain rule to calculate dy over dx. And it says dy over dx, which we're looking for, is equal to dy over du times du over dx. Now, dy over du is equal to what? dy over du is equal to d over du of this integration from 1 to u of cotangent of t dt, right? And du over dx is equal to d over dx of x2, which is equal to 2x, and that is not a problem. But this one, d over du of integration from 1 to u of cotangent of t dt is equal to what? According to the fundamental theorem of calculus part 1, because here we have d over du, and here we have the upper limit of the integration as the thing with respect to which we are calculating the derivative. We can say that this derivative is equal to this integrand, which is cotangent of t, evaluated at u. So this part, the first parenthesis, is equal to cotangent of u. Now, and the second part also, we said that it is equal to 2x, right? Now, the final result of our derivative is cotangent of u times 2x, or cotangent of x2 times 2x. Yes? So here we combined the fundamental theorem of calculus part 1 with the chain rule, and we used both of them to calculate the derivative of a integral function like this. Now, let us move on to the fourth part of this example. Part D says y is equal to integration from 1 plus 3x2 to 4 of 1 plus 2 to the 1 plus 1 over 2 plus e to the t dt. Now, we know we're supposed to use the fundamental theorem of calculus part 1. And in that theorem, the lower limit of the integration has to be equal to a constant, and the upper limit of the integration can vary. So, because we know that we need this to be true, we use the properties of the definite integrals to reverse the upper and lower limits of this integration, and we write y is equal to minus integration from 4 to 1 plus 3x2 of 1 over 2 plus e to the t dt. Okay, this doesn't work. You know what I mean. Minus the integral. Now, in order to calculate the derivative of y with respect to x, again, for this integral function that we have here, we need to consider this upper limit as another function like u and write y as minus integration from 4 to u of 1 over 2 plus e to the t dt. Now, just like the previous example, d over dx is equal to dy over dx is equal to dy over du times du over dx, and dy over du is equal to d over du of y, which is minus that integral, right? And du over dx is equal to d over dx of u, which is 1 plus 3x2. Now, we have to first evaluate the first parenthesis, which according to the fundamental theorem of calculus, part 1, is minus d over du of the integration from 4 to u of something dt, which is that thing evaluated at u, which is minus 1 over 2 plus e to the u. And d over dx of 1 plus 3x2 is equal to 6x, right? Now, the only thing that is left is to replace this u with its equivalent depending on x, which is 1 plus 3x. We do that because we want the result of our differentiation to only depend on x. So the final result is minus 6x over 2 plus e to the 1 plus 3x2. Now, guys, at this point, you have to solve exercises 3, which is part 5.4 of Thomas calculus, and you have to solve exercises from 45 to 56. And these are all exercises on fundamental theorem of calculus part 1. So now we reach to the second part of the fundamental theorem of calculus. This fundamental theorem of calculus part 2 is a theorem that gives you a way to calculate the definite integrals very, very, very easily. And this is the theorem that you use whenever you want to calculate a definite integral. And this is the theorem that lets you avoid using the definition of the definite integrals to calculate the result of the definite integrals that you have. So you don't actually need to use the limit of the Riemann sum, and you can use this theorem. The fundamental theorem of calculus part 2 says that if f is continuous at every point in an interval from a to b and capital case F is any antiderivative of F on that interval, then the integration from a to b of f of x dx is equal to the antiderivative for f evaluated at the upper limit minus the antiderivative of f evaluated at the lower limit, right? This is the theorem that you learned in the high school, and now you understand the importance of it. There are some key points with this theorem. Let us go through it. This theorem is also called the evaluation theorem, right? Why? Because this theorem reduces the concept of calculating the definite integral to evaluating its antiderivative at the upper limit and lower limit, right? Because of this, this theorem is called the evaluation theorem. Now, to calculate the definite integral of f over an interval from a to b, we need to do only two things. Find an antiderivative for f, which we call capital case F, and calculate the number f of f at b minus f at a, which is antiderivative evaluated at the upper limit minus the antiderivative evaluated at lower limit, and the result will be equal to the integration from a to b of f of x dx. Now, this process is much easier than using a Riemann sum computation. The power of the theorem follows from the realization that the definite integral, which is defined by a complicated process involving all of the values of the function f over the interval from a to b, can be found by knowing the values of any antiderivative of f at only the two endpoints a and b, right? So you understand how powerful this theorem is. Now, the usual notation for the difference f at b minus f at a is this. So instead of writing f at b minus f at a, we write capital case F evaluated at a and b. We write a line after f of x. At the bottom of the line segment, we write a, and at the top of the line segment, we write b. Or instead of a line segment, we can use something like this, right? Now, let us see some examples. Now, calculation of definite integrals has become easy for us. We have to calculate an antiderivative for the integrand and evaluate that at the upper limit and at the lower limit. Part A says y is equal to the integration from 0 to 1 of x2 plus square root of x dx. Now, according to the fundamental theorem of calculus part 2, the thing that we need to do is to calculate an antiderivative for this, which we can easily do, and then evaluate that at the upper limit, which is 1, and at the lower limit, which is 0, and subtract these two values. Now, what is the antiderivative for x2 plus square root of x? it is 1 over 3 x to the 3. The antiderivative for x2 is 1 over 3 x to the 3 according to the power rule. And the antiderivative for square root of x is, because the square root of x is equal to x to the 1 over 2, the antiderivative for it is x to the 1 over 2 plus 1, which is x to the 3 over 2 over 3 over 2, which becomes equal to 2 over 3 times x to the 3 over 2. Now we have to evaluate this antiderivative at the upper limit and at the lower limit and subtract the values. The evaluation at the upper limit is this: 1 over 3, 1 to the 3 plus 2 over 3, 1 to the 3 over 2. The evaluation at the lower limit is 1 over 3, 0 to the 3 plus 2 over 3, 0 to the 3 over 2. Now, this first part is equal to 1 over 3 plus 2 over 3, which is 1, and the second part is 0. So the final result that we're going to get is 1. Now, the next one, part B. The definite integral of sine of 2x from 0 to pi over 8. Now, the first job is to find an antiderivative for sine of 2x. What is the antiderivative for sine of 2x? It is minus 1 over 2 cosine of 2x. And we have, according to what you saw, we can write this line segment, and at the bottom of it we write the lower limit of integration, and at the top of it we write the upper limit of integration. So this is equal to minus 1 over 2 cosine of 2x at pi over 8, which we have here, and the result negative cosine of 2x evaluated at the lower limit, which is cosine of 0. Now, the first part, cosine of 2 times pi over 8, is cosine of pi over 4. Cosine of pi over 4 is equal to what? Square root of 2 over 2. Cosine of 0 is equal to what? It is equal to 1. So the final result is minus 1 over 2 times square root of 2 over 2 minus 1, which is equal to square root of 2 minus 2 over 2. And if you put into effect this negative sign, you're going to have minus the square root of 2 plus 2 over 4, which is your final result. Yes? Now, let us move to part C. In part C, y is equal to the integration from pi over 4 to 3 pi over 4 of cosecant of theta times cotangent of theta d theta. Now, what is the antiderivative for cosecant cotangent? The antiderivative for it is minus cosecant. Now, according to the fundamental theorem of calculus part 2, you have to evaluate that at the upper limit and at the lower limit. Now, here we used a trick because here we have a negative sign. We want to get rid of it. How do we do that? Instead, we can ignore this negative sign and replace this lower limit with the upper limit. So the result of this minus cosecant of theta evaluated at 3 pi over 4 and pi over 4 is cosecant of theta evaluated at pi over 4 and 3 pi over 4. And the result of this final one is cosecant of theta at pi over 4 minus cosecant of theta at 3 pi over 4. And cosecant of theta at pi over 4 is equal to 1 over sine of pi over 4. And cosecant of 3 pi over 4 is equal to 1 over sine of 3 pi over 4. Sine of pi over 4 is equal to what? It is equal to 1 over a square root of 2. So 1 over a square root of 2 becomes square root of 2. Sine of 3 pi over 4 is equal to what? 3 pi over 4 ends up in the second quadrant. So sine of 3 pi over 4 is equal to sine of pi minus pi over 4, which is equal to sine of pi over 4, right? So for this second one, we also have 1 over a square root of 2, and 1 over a square root of 2 is equal to a square root of 2, and the final result turns out to be equal to 0. Now, let us go through part D. Here, we have to calculate the definite integral of dx over 1 plus 4x2 from 0 to 1 over a square root of 3. Now here we have dx in the numerator. But what does that mean? It means that we have a 1 here that we have omitted, and we have multiplied it by dx. Now, our job is to find an antiderivative for 1 over 1 plus 4x2. How do we do that? 1 over 1 plus 4x2 is equal to 1 over 1 plus 2 to the 2 x to the 2, right? Now, do we have an antiderivative for this or not? If we didn't already have an antiderivative for this, our job would be difficult. But we are lucky, and if you look at this antiderivatives table in the beginning of this chapter, you see the antiderivative for 1 over 1 plus k to the 2 x to the 2 is 1 over k arctangent of kx. So the antiderivative for 1 over 1 plus 2 to the 2 x to the 2 is 1 over 2 arctangent of 2x. Now, using the fundamental theorem of calculus part 2, we have to evaluate that at 0 and 1 over a square root of 3. That would be equal to 1 over 2 arctangent of 2 times 1 over a square root of 3 here, minus arctangent of 2 times 0, which is arctangent of 0. Now, arctangent of 0 is equal to what? The arc for which the tangent is equal to 0 from minus pi over 2 to pi over 2 is 0. So this term here, this second term, arctangent of 0 is equal to 0, and you omit that and you write 1 over 2 are tangent of 2 over a square root of 3. And you can use a calculator to evaluate this one. It is not necessary. This is a determined value. It is not necessary for you to come up with the exact number. It is better if you do. Now, part E. In part E, you have to calculate the definite integral of 1 over x minus e to the minus x dx. What is our job here? Now we know that our job is to come up with an antiderivative for 1 over x minus e to the minus x. Now, we come up with our antiderivatives one by one. What is the antiderivative for 1 over x? It is ln of x. And what is the antiderivative for e to the minus x? It is minus e to the minus x. If we multiply the negative sign that appears with this negative sign that exists, we're going to have plus e to the minus x, right? Now we have to evaluate ln of x plus e to the minus x at the upper limit and the lower limit. The evaluation at the upper limit is going to give us ln of 2 plus e to the minus 2 here, and the evaluation at the lower limit is going to give us ln of 1 plus e to the minus 1. Now, here we can do some simplifications because ln of 1 is equal to what? It is equal to 0. So the things that remain are 1 ln of 2, 1 over e to the 2, and 1 minus 1 over e. This is your final result. And you can, if you have a calculator, as an exercise, you can use the calculator to actually evaluate this ln of 2 plus 1 over e2 minus 1 over e, right? Now, let's go to the to the part F of this exercise. It says calculate the integration from minus 4 to 4 of absolute value of x dx, right? This example is a little bit different from the other examples. What is the difference? We have to come up with an antiderivative for absolute value of x. But if we look at the antiderivatives table that we have, we don't have an antiderivative for absolute value of x. But we know that we can determine the behavior of this absolute value function for different values of x. And here we see that x is changing from minus 4 to 4. So, if we divide this integration into two integrations, that in the first one, x only has the negative values, and in the second one, x only has the positive values, then our problem with this absolute value function is solved. So we do that, and we go ahead and write the integration from minus 4 to 4 of a absolute value of x dx is equal to the integration from minus 4 to 0 of that plus the integration from 0 to 4 of that. We know that we can do this using the we know that we can do this using the properties of the definite integrals, right? Now, in the first integration, the absolute value of x for the values of x that are from -4 to 0 is equal to negative x here. So the first integral here is equal to this. And for the second integral, that the integration from 0 to 4 of absolute value of x dx, we know that the absolute value of x is going to be equal to x for the values of x that are positive. So the second integral here is going to turn into this integral here. Now, here we have two very simple integrals to calculate. For the first one, the antiderivative for minus x is -1 over 2x to the 2. And we have to evaluate that at 0 and -4. And for the second one, the antiderivative for x is equal to 1 over 2x to the 2. And we have to evaluate that at 4 and 0. Now, just for the sake of convenience, we change this first one to this. Here we had a negative sign, and we hate negative signs because it complicates our evaluation, and uh, the probability of making mistakes increases. So we ignore the negative sign and we replace the upper and lower limits. And we write 1 over 2 x to the 2 evaluated at -4 and 0. So if we continue with the calculations, 1 over 2x to the 2 evaluated at -4 and 0 is 1 over 2 times -4 to the 2 minus 0 to the 2, right? And for the second one, just like that, 1 over 2 4 to the 2 minus 0. So you're going to have 8 plus 8, and the result is equal to 16, right? So whenever you have something depending on the absolute value in the integrand, what do you have to do? You have to divide up the interval of integration into subintervals in which the integrand is positive or negative. Okay, so that we can get rid of this absolute value sign that we have. Guys, now we are trying to review what we've learned so far, and we want to distinguish the differences between the definite integrals and the indefinite integrals. The one very important point that you have to keep in mind is that a definite integral, which is the integration from a to b of f of x dx, the result of this integral is a number, right? But for the indefinite integrals for which the limits of integration were not clear, the result of the integration was a function plus an arbitrary constant c, right? So here, by knowing this, we can have another interpretation of the evaluation theorem. and that is, if we want to calculate the definite integral, we can first ignore the limits of integration and calculate the integral in the indefinite form, which basically is finding an antiderivative, and then evaluate the antiderivative at the upper and lower limits and subtract them, right? So by this understanding, there's not much difference between the indefinite integrals and the definite integrals, although there is a word of difference between their definitions, right? Very good. Now, guys, you have to go through uh, these exercises. The next week, you also need to solve part 4 of your exercises, and they are exercises from 1 to 34, even numbered exercises excluded, 12, 30, and 32. So you only have a very a small number of exercises here, 14 exercises on on definite integrals, and they are from part 5.4 of Summers Calculus. Now, up to this point and after these exercises, you see that we've only been able to find antiderivatives of functions that are clearly recognizable. But not all the integrands of the integrals we want to calculate are that simple. And we need to begin to develop more general techniques for finding antiderivatives. More general techniques for finding antiderivatives. And the first technique that we get introduced to is called the substitution method. Guys, part 4 of the chapter of integration is dedicated to techniques of integration, and these are techniques that you're going to use in order to evaluate more difficult integrals. And the first technique that we're going to talk about here, as we said, is going to be the substitution method. Now, we describe the substitution method to evaluate the following integrals. If you have an integration in the form of the integral of f of gx g prime of x dx, then if you do a substitution in the form of considering this gx here as u, then what do you have? This g prime of x dx, which you have here, g prime of x dx, is equal to what? G prime of x dx is equal to du over dx times dx, and that is equal to what? That is equal to du. So what does this mean? This means that the integral that you have is going to be integration of f of u du, right? and it is gonna, by changing gx to u, our integral here is gonna turn into integration of f of u du. Now we have to integrate this with respect to u, and in the final result that we're gonna get, we're gonna replace u by gx. Yes? This method is called the substitution method because we are considering some part of the integration as u, and we are substituting that part with u in the final result. Now, let's look at example 15. It says, calculate the following integrals using the substitution method. Now, look at part A. Here we have integration of x3 plus x to the 5 times 3x2 plus 1 dx. Now, how do we use the substitution method to calculate this integral? We have to choose some part of the integrand and call it u. Now, the answer to how do we know which part to choose as u is something that doesn't have a general rule, and you have to find it by experience. Now, let's see what happens if we consider this part x3 plus x as u. If we consider x3 plus x as u, then du over dx is going to be 3x2 plus 1, and 3x2 plus 1 dx, which is what we have in the rest of the integrand, is going to be equal to du. So integration, the integration that we had originally, is going to turn into a very simple integration. Integration of x3 plus x to the 5 times 3x2 plus 1 dx is going to turn out to be equal to integration of u to the 5 du. Why? Because this part is u, so u to the 5, and this part is du, right? So for this integral, we can easily calculate the result, and it is u to the 6 over 6 according to the power law. And now at this step, we have to replace u with the function of x it stood for at the end, and it is x3 plus x. So the final result is x3 plus x to the 6 over 6 plus c. Now, the second example. Here, we want to calculate the integration of a square root of 2x plus 1 dx. Now, at the first glance, it might not be clear which part to choose as u. But let us choose 2x plus 1 as u. If we do that and consider 2x plus 1 to be equal to u, then du over dx becomes equal to 2. So dx, which is the rest of what we have in front of the integral here, is going to be equal to 1 over 2 times du, right? What are we trying to do here? We are choosing one part as u, and we are trying to rewrite this integral in terms of u. So everything else that we have also has to be written in terms of u. So 2x plus 1 equal to u, dx equal to 1 over 2 du. If we replace these two into the original integral that we had, we're going to have integration of a square root of u times 1 over 2 du, right? Now, this integral is equal to what? This integral is equal to 1 over 2, the integral of a square root of u du. And this one can be easily calculated. The integral of a square root of u, which is equal to u to the 1 over 2, is equal to 1 over 2 times u to the 3 over 2 over 3 over 2 plus c. Now, if we do the simplifications, we're going to reach to this. And we have to remember to replace this u with the function it stood for originally. So we have to replace u with 2x plus 1. If we do that, we're going to get this. And you have to be absolutely careful not to forget this plus c sign when you have an indefinite integral, right? Up to this point, in parts A and B, when we were using the substitution method to calculate the value of indefinite integrals, at the end we saw c. But if we had upper and lower limits for these indefinite integrals, then we would have definite integrals. And when we find the antiderivative at the end of this process, this is an antiderivative for the integrand. We can easily use this antiderivative to calculate the value of any definite integral that we might have. Yes? Similarly for this example. So guys, that is it for today. And for the next week, you're gonna have to solve exercise set of 3 and 4 as your next homework. Thank you all very much. See you next week. Actually, see you in the Q&A session. Okay.